So yesterday, we were covering an example and we showed this truth table. And once again, once we start getting into compound logic gates, truth tables get hairy and scary. And it's much easier to represent the canonical expression, whichever one is easiest, either the standard expression in cases where the only result is true, or in other cases where the only expression is false, right? So I'm going to go ahead and change these inputs to A and B just so that we can use those as a reference for our, and I'm just going to use A and B, okay? So our canonical, yes? Our canonical expression for an AND would take, and once again, from our example yesterday, we used a not to flip it, flip the output. We'll get to that in a second. But the initial output values, the initial outputs, going to use the Luke rule, all together, the outputs, plural, are represented in standard font. They're not the bold font. So 0, 0, and 0 and 1. So our canonical representation for a logic gate that uses A and B inputs would be what? Anyone? Would we use standard or reverse?
Reverse.
Well, if we used reverse, we'd have to state this case and this case.
Okay.
It would have to be standard.
Standard.
Standard is correct.
Excuse me?
Oh,
Can you explain when we use reverse and when we use standard?
That's an excellent question, and I'm so glad that you asked that question. We've covered this before in previous classes, but in case you're joining us now in a renewed, we've circled around. So one thing we do in our course is we use spiral curriculum, which means we circle around kind of like a big shark. You take a bite and then you come back a couple of weeks later and you take bigger chunks. So whenever you're trying to be the most efficient and you want to represent the behavior of a Boolean function or a logic gate, you can state the cases where the output is true or 1. That's the standard form, and in this case, the most efficient way to do it. If we chose to use the reverse case, we're going to be writing out expressions of A and B inputs that are false or 0. So you choose, when you're looking at the truth table, you make a decision. Which one's going to involve less work? Writing out the single case that's true, or writing out the 3 cases that are false, which would be a reverse canonical, 3 reverse canonical expressions for 3 false outputs, plural. Does that answer your question?
So essentially, when most of it is 0, we use reverse. Most of it is 1, we use standard. Essentially.
If the least number of outputs is 1, then you would use standard. If the least number of outputs is 0, then you would use reverse. So we'll see a case that works for reverse in just a moment. So the original input values for A, and does that answer your question? And this is Schneider, correct?
Yeah, Schneider.
Okay. Yeah, the voice recognition, I'm working on it, right? So we're doing this online, and I don't have the screen up, so I can't see which mic is active, but all right. Thank you, Snyder. Okay, so our canonical expression, our standard canonical expression for a plain AND logic gate or Boolean function with 2 inputs would be what? Anyone? A, B. Do we put any ticks there? The only true output here the input value for A is 1, and the input value for B is 1 or true. So do we need to put any ticks down in this expression?
No.
No. No.
No, that's it. So if you see AB, and let's just standardize on inputs that are A and B, you know? The standard canonical expression, right? We're going to say standard canonical expression is AB. Okay? I'm going to go ahead and save this, and now I'm going to do a save as. So I just want to make life easy. And I'm going to call the save as and canonical. And I'll use std for standard. And now I'm going to do a save as because I want to flip it. So now I'm going to take the case of a NAND. And we're going to say reverse canonical. Can everybody see what I'm doing here with the name? So actually, now we're looking at flipping. What happens when we flip the AND values by putting a not in front of it. So what do I mean by that? We're saying that we have something that looks like this. Remember, whenever we have parentheses, whatever's going on in the truth table, we apply universally to all of the collective outputs that result from the AND function or operation. Luke, are you in the audience?
Yep.
Okay. Am I doing better with that explanation?
Yeah, it's fine.
Okay, good. All right. So in this example, we notice that we've flipped. That's why they're bold. So in the previous example, I guess what I should have done in the previous example, let's do that. Just to be completely correct, let's do this in our previous example. So it's a little clearer. We only have one set of outputs. I was reusing the thing we were doing yesterday. My bad. Okay. So, all right, but I'm going back to this one. Now that I have a not and it applies to the outputs, all of the outputs, I have flipped the outputs now. So am I interested in doing a standard expression of the canonical because it's less work, or should I do the reverse canonical expression because it's less work?
You do the reverse.
Yes. Was that Tiana?
Yeah, that was me.
Excellent. Okay. Once again, voice recognition. Okay. So we're going to do reverse canonical expression, and we need to note the original input values for A and for B. So what do we write for our canonical expression? Can we put the same thing there for our canonical expression? No.
Put on A tip and B tip.
Okay, that's a great suggestion. But if I put A tick and B tick, I'm saying that the output was 0 when the A input was 0 and the B input was 0, and that means I'm calling out this particular specific output out of all of them. I only have one case that's false or 0. So here's the point. They're both AB, both of them, except that for NAND, right? So we're going to say AKA NAND. It's reverse. It's the reverse canonical, which tells you when A is true and B is true, my single output is false. I don't have any other expressions, just the one, A, B, true and true. So when A is true and B is true, the output is false. right? And that's what I have here. Are there any questions? I'm going to go back to this, do the same kind of stuff that I did to highlight that. So if you see standard canonical expression, we're talking about outputs. Every output could be a single output, could be multiple outputs, but each output that results in a true, and then in the reverse, we're looking at each output that is false. And because the not is applied, it flips, it's a wild card. Any questions about and NAND?
No questions.
Okay, so I have a trick question for you. And or are sort of like opposites. And is the most restrictive because it's the least often that an output is true. In more cases, the output is false. So in terms of wanting a true output, if you want a true output, the ands are the most restrictive and the ors are the least restrictive. If I do OR now, am I going to see a result that looks just like NAND? In other words, here's my question. Will my canonical expression and my outputs work just like OR? Because I'm putting a not in front of AND. It's like I'm flipping AND. Does that mean it behaves exactly like an OR? That's the question. What do you think? We've already hinted at this in the class, in a previous class. What do you
No, it would not behave the same.
Correct. It would not. We'll show you right now. And let's see, who was that speaking?
Luke.
That was Luke. Okay. All right. Good job, Luke. So we're going to do this and save as or. Let's do the or standard canonical now. Okay. So I'm going to save as. And do I want to use the standard canonical or do I want to use the reverse canonical?
Reverse.
I want to go out on a limb and say reverse. And I'm glad you said that. Was that Luke again?
Yes.
Okay, so I'm going to say reverse, and here's why. So, and I don't know if this is true or not, so I'm going to highlight that. I don't know if that's an accurate expression. But let's look at this again. My output has to change. All of my outputs have to change because I'm dealing with an OR with A and B. So I have a case where A or B is, good afternoon, Keandre. Good afternoon, Keandre. Okay, glad you could join us. All right, so in this case we have a false input for A or a 0, false input for B. Even though we have an OR, we can't put a true there because neither A nor B. See, that's the word now. Instead of and, it's or, right? So neither A nor B or B are 1, so that's a 1. But in this case, if A is 1 or B is 1, then the output is 1. So I'm going to flip this. I'm not because I'm using a not, but just because that's the case. The A is false, but the B is true. So if A or B is 1, then the output is 1. If A or B is 1, then the output is 1. And if A or B is 1, then the output is 1. Everybody with me so far, yes?
Yes.
Okay.
Yes.
Okay. So which is easiest to do, the reverse canonical or 3 stated cases of the standard canonical?
Reverse canonical.
The reverse canonical is correct. Who said that?
Luke.
Luke. All right, good. Now, so we have to list in our expression the A and B values for our canonical expression where the output is false. And the original inputs for A and B where the output is false, because we're doing reverse, that's the easiest case. A is false and B is false, or 0 and 0, so I'm going to put a tick and a tick. Now remember my question? If I put a not in front of and, it's like reversing the behavior of an and is the most restrictive, and or is the least restrictive. So does that mean a NAND is going to behave like an or? Well, kind of, okay? And here's what I mean by kind of. Here's or, and here's NAND, okay? So the reverse canonical is AB for a NAND, and the reverse canonical is A tick B tick for an OR. So there is some similarity there. We're going to be stating the false cases more often because that's easier. But the input values are different, right? So your inputs have to be false and false in order to get the reverse canonical expression. Now we could state the standard expressions, plural, all three of them. A tick B, A B tick, and AB, if we wanted to go to all the trouble of stating the standard canonical expressions, but it's a lot more work. What we want is the single, clearest, simplest, most straightforward statement of behavior of what that thing does. Any questions so far about and, NAND, and OR? Any questions?
So is okay. I have a question. So does the one NAND behave like an AND?
Okay, so your question was, and I just want to make sure I understand the question, does the AND behave like a NAND? And
NAND behave like an AND.
the NAND, so to answer your question, the AND behaves in a similar fashion to the NAND, except that with AND, the only output is the only one output that you get that's unique is true, and with a NAND, the only one output that you get with a NAND is a false. So they're similar in behavior.
With the one reverse and we reverse canonical expression and the one standard one.
Correct. Not uses reverse, and uses standard. Because there's fewer of them. Whichever one is fewer, whichever case is more unique, right? There's only one value that's 0, so that's the most unique value. Let's go on to NOR. Any questions about? Any questions yet about? All right, so any other questions before we go on?
No questions.
Okay, so here's the thing. I want you to memorize. And the canonical expression is AB, and it's a standard canonical expression. I want you to be able to match that. Or the reverse canonical expression is A tick B tick. That's the canonical expression that matches the behavior of OR. NAND. The reverse, it's reverse, right? It's a reverse canonical expression because the most unique output, the only one that's false, is AB. So I want you to know that it's AB. Let's look at NOR. So now we're going to look at NOR. I'm going to save as. And I'm not entirely sure. Would anyone care to predict whether it's going to be reverse or standard? Well, OR was reverse, so NOR might be what? What do you think?
Standard.
I'm going to say standard. I'm just going to spitball here. Yeah, I would agree. So I'm going to say standard here. And I'm going to say NOR. And I'm going to say AKA not or, right? I don't know if this is true. I don't know if this is accurate right here, but that's what we're going to figure out. So OR is going to result in this output initially. That's what OR is going to do. But because we're going to knot each one of these down the row, I'm going to make this bold. And then what am I going to do to the last three? Anyone?
All zeros.
All zeros. Yes. Excellent. So, and 0. Which is easiest to express, the standard or the reverse? Which one is less work?
Standard.
Standard is correct. Because there's only one unique output that's true, and it's true when the A input is 0 or false, and the B input is 0 or false. Therefore, my canonical expression, my standard canonical expression is A tick B tick. So, what I have is a case where, well, let's see, let's open up the last one. We have NAND, NOR, and AND. We need the OR open. So let's open the OR as well. So we have all 4 of these. So the OR is AB, but it's reverse canonical. The NOR is AB, but it's standard canonical. Does everybody see that? Let's do that again. The OR is A tick B tick, but it's reverse canonical. The NOR is A tick B tick, but it's the standard canonical expression. Everybody see that?
Yeah.
So if you get
Yes.
if you get the first case right, if you get the first set of criteria correct, you say, okay, I know OR is reverse, and it's A tick B tick. If that's your anchor, and you say, well, what's NOR? I'm going to flip it.
Excuse me.
I'm flipping reverse versus standard. The
Excuse
values,
me.
the input values don't change. Yes, there was a question.
So like the ticks, right? Ticks represent the zeros, right?
Ticks represent the 0 value input for A and the 0 value input for B. Correct.
Yeah. Just double check.
Yes, glad you did. Let's look at the AND and the NAND. Here's the AND. AB, standard. What do you suppose is going to be different with NAND? Is it going to be the same?
No, it will be.
Excuse me. So what should the lack of ticks for this one?
All right, the lack of ticks for this one is because with a standard canonical expression of AND, we're looking for the outputs that are true, and there's only one unique value that's true, where the A is 1 and the B is 1. And since they're 1 and 1, we don't use a tick. We only use ticks when they're 0. Okay?
All right.
Does that answer your question?
I think I got it now. Yeah.
Yeah. We get these 6 solid. We get these 6 solid. We have the building blocks to create a universe. So we're close. This is
So you
exciting.
like highlight those ones. But I know that's the one that's being taken effect. Yeah.
All right. Yeah, I'll do that if that helps.
Yeah.
And then I'll make that bold and I'll highlight that too. How's that?
Yeah. Then.
All right. We'll do the OR like that as well. So we'll highlight the reverse case, and we'll bold this and highlight that, right? We'll do the same for NAND and NOR. Any questions before we go on?
Yeah. Are you gonna be uploading these up to Blackboard?
Oh, you bet. Absolutely.
Yeah. Thanks.
Yeah, absolutely. Okay, so let's do XOR. And that's the last one we're doing. And then we're going to talk about pins and all that stuff. All right, so it's these two, and this one. All right. So I took the liberty of oh my, hang on. I took the liberty. I'm going to pause the recording for just a second. Thank you so much. So I took the liberty of tying my iPad into the demo because I want to show the textbook, and I also want to do a little bit of drawing in a minute. So this is the implementation view, not the interface view, because it's not just showing A and B and the output. It's showing all the guts inside, all the implementation components to make this XOR happen. Now remember, in our previous class, we said an XOR that is promoted greatly by the authors of your textbook involves two ands, two nots, differentially applied to different inputs, and all of that output feeds into an OR, and that's what gives you the behavior of an XOR. But this is the part I want you to see that I think is really cool. This is the truth table. The truth table here that we're seeing right here with A and B and out. Which cases are true? When the inputs are the same or the inputs are different?
When the inputs are different.
The inputs are different. So if I'm trying to mark on this, but I can't really mark on it with a stylus. If you look at the first A, if you look at the two values first, A is 0, B is 0, the out is 0. So when A and B match, when they're the same, when they're identical, when the inputs match, the output is false. Let's look at the last case. A is 1, B is 1, the last row on the right. The output is false again. So whenever you have matching inputs, you get a false. But if you have different inputs, any of the inputs are different from any of the other inputs. So if we had a 10 input, we had a 32 input XOR, a 64-bit XOR, not a 64 input Boolean XOR function. 64 columns. Oh my gosh, 2 to the 64th truth table. Oh, that's just crazy, right? What you're going to find is that there's only a couple of cases where all the inputs and all the outputs match. But in other cases, in most of the other cases, the vast majority of the cases, at least one of the inputs is different. So an XOR is going to be false when everything's 0 or everything's 1. And that's a unique behavior. Very useful behavior with encryption, with networking, and we're going to share more examples about that. But we're going to go back to our other screen now, and we're going to go ahead and do the truth table for this, okay? Now that you've seen this. So I'm going to stop sharing. Any questions before I stop sharing?
No question.
That's what this gizmo does here. That the and or with two nots, two ands, and an or, right? And the coolness is everything you build is going to be different. Yeah, so we're going to get to the special place at some point where we start talking about the logical expressions or statements, programming statements that we can derive from that. But we're going to do that in another class. Okay, We're going to shift a gear. I'm going to stop sharing and let's see, where are we? Come on. Give it to me. Stop. Okay. So now I'm going to go back and share again. And I'm going to open up OR. Because I think that one's, no, let's do this one. We're going to modify this one. Because we've already got a second set of values there. So I'm going to change this, save as XOR. But I don't know if it's going to be standard or canonical. It could be standard or canonical because you could decide I'm going to represent the cases that are true, or I'm going to represent the cases that are false. Now, I just explained that if you had 64 inputs, only 2 of them would be false. All zeros or all ones, the very first row and the very last row. And you could have 2 to the 64th rows in that bad boy truth table, and it would take you a month, and you wouldn't have any dates, and you couldn't pause for snacks. It would be terrible. Okay, all right, I'm sorry. But the point I'm trying to make is that you definitely want to go reverse canonical here because there's only 2 cases that are false. So I'm going to say reverse. Right? And here's the catch. If I say XOR, I'm not going to worry about the statement of logic in our textbook, but it's in there in your textbook, okay? And I could, let's see. Yeah, no, I'm not going to put that out there right this second because it's a little thorny. So what am I saying? I'm giving you the tools to work the easiest way, the most efficient way. Sometimes that's writing a logical statement. Sometimes that's writing out the canonical expression. Sometimes that's doing a truth table. Sometimes that's drawing a picture of a physical logic gate that's built in electronics. Other cases, it's using a Boolean function. You're going to pick and choose whichever is easiest to work with. So I'm going to go ahead and nix this. And then let's start over here. And we have 2 expressions we have to accommodate. But let's make sure we're dealing with it. So 0 and 0 in the book, it said the output was false, and then 0 and 1, the output was true. And then 1 and 0, those are different, so the output is true. So, and then 1 and 1 is 0. Now, I could say that there is a nice simple way to state this in a program. You could say if A is not equal to B, then out equals false. Else out equals true. That's another way we can do it with a simple pseudocode statement, and that's much cleaner and easier to understand than the algebraic expression, the Boolean function provided in the textbook. In any case, we're going to stick with reverse canonical expression because if we had 3 or 4 or 5 inputs, the larger this table would grow. Only the first one would be false, and only the last one would be false. And what we have here is a case where the trues come first, and the falses come last. So that's our expression. That's what I want you to remember. Just the first and just the last. My reverse canonical expression for XOR is AB or A tick B tick. It's reversed because those outputs are each of those outputs is false. Okay, so I'm going to do what was it Schneider asked me to do? Highlight these, right? Okay. Any question about this?
For that programming statement, isn't it supposed to be the other way around?
The programming statement. If A is not equal to B, so in this case, if A is 0 and B is
Excuse me?
1,
Oh. Why is the bottom row 0 instead of 1?
oh, you're right. Good catch. Who was that?
Oh, Snyder.
Schneider?
Luke.
Yeah.
So who called that out first?
Luke.
Luke.
Luke. Man, I'm gonna have to post additional credit because you caught a mistake that I didn't see, and no, you're absolutely right. If A is not equal to B, that's the logic, right? As long as one of the inputs doesn't match all the other inputs, right? Then out equals 1, else out equals 0. Okay, yeah, that is correct. Thank you, Luke. Okay, everybody good? Are we ready to move on to the reverse or the XNOR? I'm going to go ahead and do a save as. Do you think that XNOR is going to be reverse or standard? What do you think? I'm going to say standard.
Yeah, based on the pattern.
Based on the pattern, based on the behavior, right? So I'm going to say XNOR, aka not XOR, right? So I'm going to say this is standard now. Canonical expression. And here's the fun part. So let's go back and make this so we're starting over here with a fresh table. In the previous one, we had 0 and 1 and 1, and then 0 with XOR, with a reverse canonical expression. But in this case, the NOT is sitting outside the XOR, so it's going to take each output, all of the outputs together, right? And it's going to reverse them. So that's what I get here and here. And then what do I get here?
Zeros.
Zeros and zeros, yes.
Wait. No, that the one standard canonical expression will be reversed.
Standard. So
Yes.
Lacraine, standard means that we're going to be looking at each case of output that is true.
Oh, so it would be the one we reverse canonical expression.
Actually, yes, it would. So what we would end up doing is taking this and putting it here, taking this and putting it there, if we're listing them in order, right? So basically, when A is 0 and B is 0, then the output is true. That's what we mean by standard. It's true, right? And when it's 1 and 1, it's true, right? That's what we get. If we have more than 2 inputs, huge number of inputs, 64 inputs, or well, let's just use 8. So to the 8th, we have 8 inputs, we have 64 possibilities on the truth table. Oh my gosh, that's a truth table with 9 columns, 8 inputs, A, B, C, D, E, F, G, H, and then there's an output. Huge thing. What we end up with is still the same simple pattern. Only the first and the last end up being true when the inputs are the same. When the inputs are different, the output is false. That's the behavior. So if the inputs are different, the output is true for an XOR. If the inputs are different, then the outputs are false for an XNOR. So the statement of logic I had there, Luke, you know, I was just getting ahead of myself, right?
Right, yep.
That's all I was doing. I was just getting ahead of
Yep,
myself.
that was the XNOR.
You don't believe that, do you? No, I don't either. I'm just trying to tap dance here. So what I would do in this case is I would flip it like I had it before in my original statement. If A is not equal to B, then out equals false, else out equals 1. That's the pseudocode logic. That's what I could put in a programming statement if I wanted to test it in software, right? And what I get is A tick, B tick, or AB for the standard canonical expression. So let's look at the difference between the XOR and the XNOR. Almost the same. For the reverse canonical expression, AB or A tick, B tick. For the XNOR, for the standard canonical expression, A tick, B tick, or AB. Now, in the final analysis of things, the order that these are listed isn't that important. What's most important to understand, the big difference here is all the outputs are true. In this case, all the outputs are false. Everybody got that? Okay, so
Yeah.
I want you to be able to match. If I give you a set of canonical expressions, I'm going to give you this, and I want you to give me, is it an XOR? Is it an XNOR? Is it an OR? Is it an AND? Is it a whatever?
But why are you keeping the bottom output still 0? Because of the not?
Okay, can you repeat the question?
The bottom output you have for the
This-
bottom right still 0.
This
One.
one?
Yeah.
Okay, because we're dealing with the XOR, not the XNOR. So in the last example that we covered, XNOR, that's the standard canonical expression. We're focused on what becomes true, and when the inputs all match with XNOR, you have a true input. With XOR, the behavior is different. It's the reverse of that. When all the inputs match, the output is false or 0, and it's the first case and the last case that result in a false output because all the inputs match, A and B. And it wouldn't matter how many inputs we have, 2, 8, 16, 32, 64 inputs. If they all match, the output is false for an XOR. If there's anything different, you can have, let's say we have 64 inputs. If 63 of them are false and 1 is true, it's a 1. It's true. So an XOR with however many inputs, if there are any differences for any of the inputs, it's going to say, oh, true, we have a difference. Where the XNOR says, true, or false, they're all the same. So yeah, that expression I just said was what? For any of the inputs that are different, we're always getting a false, and there's lots of them. The easiest expression or the quickest way to state the logic is to just look at the cases that are the least common or most unique. For the XNOR, the first and the last are the least common. They're the most unique, and they're true. So if there's any differences in the inputs, an XNOR will say false. False. The inputs are not all the same. If there are any differences in the inputs, the XNOR will say false. The inputs are not the same. In terms of stated logic, in plain English, that's what it's doing. And that's the reverse of what an XOR does. An XOR says, true. At least one of those inputs is different than all the others. That's what an XOR does. So it lets you detect, this is important, it allows you to detect whenever you have a true case where at least one of the inputs is different. It's like a difference radar. Does that make sense? If I have a huge truth table and I have 64 inputs and I have, oh my gosh, 2 to the 64th rows, I have 4 billion rows. No, half of that. No, that's not right. What's 2 to the 64th? Whew, that's a really big truth table. Let's see. Yeah, let's just do that. 2, y to the x, 64. Oh yeah, so that's million, and that's billion, and that's trillion, and that's quadrillion, and I think that's quintillion. 18 quintillion, 446 quadrillion, blah, 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 right? That's however many rows in that truth table you have. But if any of the inputs for any of those are different than any of the other ones, bloop, it's true, which means you can detect even very minor differences, very small differences. This is powerful because in analytical science, when you're dealing with chemistry or physics, you may have very small values that you need to detect, like however many beta particles or however many alpha particles. You want something that's going to light up and go, hey, I've got a difference. That's what we're doing here. That's the significance of what we're doing here. Okay, so what have we accomplished today? We're getting on the boundary of our class session. We were able to match the basic logic gates with their canonical expressions, and we developed each of those for OR, and NOR and NAND, and then XOR and XNOR. On Monday, here's what we're going to do. We're going to pick up the trail, and we're going to do the rest of this on Monday. Yes, we had a question.
There like a chapter in the textbook that explains this section in deeper detail.
Yes, the reading that I've assigned in the first, second, and third module, it all touches on some of this, but it's stated in very concise, very short terms. When the C programming language was created, Kernighan and Ritchie were the two gentlemen that created the C programming language. And they wrote their first book about the C programming language, and it was like, I don't know, 60 pages. And it's still being used today as a reference to learn C. because it was written by the guys who designed it, and it's really, really meaty. It just takes a lot of time to digest and break down. And that's why we're investing so much time to break this down. So I would encourage you to go back and take the same sections that we're assigned reading and then go over them again. And now that we've been over this, some light bulbs are going to come on, because you're like, oh, yeah, now I get it because of what Professor Kentop or what the students said about such and such. So that's why we use that spiral curriculum. We come back around as a shark and take a bigger, deeper bite. If we get to the point where we know the behavior of just 6 components, or, and, well, you got to include not, right? So let's make it 7. Not, or, and, NAND, NOR, XOR, XNOR. Once you know those, you can build anything. You can do anything in the digital universe. And we're right there. We're right at the edge of that. That's what we'll take up on Monday.